We take so much for granted in this modern world. You turn on the faucet and water is going to come out. You go to the grocery store and there are going to be stacks of oranges and grapefruit. Any time of the year, you turn on the light switch and the lights are going to go on. A century ago, you wouldn't have been quite so blasé about these everyday occurrences. Indeed, all of these simple modern marvels and so many more are a consequence of a great scientific principle, that electric currents are produced by moving electrons in a closed path. This lecture is divided into two parts. First, I'm going to tell you about the surprising history of the invention of the battery, which was invented in Italy more than 200 years ago. Then we're going to look at the design of electrical circuits and their principal components, that is, a source of energy, a device that does something interesting or useful, and finally a closed loop of conducting material, usually wire, to complete that circuit. The last lecture I introduced the idea of static electricity. Objects, they obtain static electricity when they have either an excess or a deficiency of electrons. So electrically charged objects then can exert forces on each other. We saw that opposite charges attract each other. Like charges, two negative charged objects or two positive charged objects repel each other. You can do lots of simple experiments to study this phenomenon and document the details of static electricity, and indeed even come up with a quantitative description of it, as in Coulomb's law, that the force of static electricity is equal to the charge of the first object times the charge of the second object divided by the distance between them squared. But static electricity, while it's intriguing, is rather limited in its practical applications. Most modern uses of electricity rely on electric charges, that is, electrons that are in motion. Newton's first law tells us that if electrons are going to move, if we're going to put them into motion, you need to apply a force. And it was not until 1794, when Italian physicist Alessandro Volta invented the battery, that such a force was readily available for people in a laboratory, and then eventually people in our homes and businesses as well. So at this point, I first want to introduce two astonishing characters in the history of science, Volta and his fellow countryman Luigi Galvani. Their careers were linked in this curious sort of way, and they were linked because of the behavior of frogs, of all things. Alessandro Giuseppe Antonio Anastasio Volta. He was the fifth of 5 sons born to an impoverished family of lesser nobility in northern Italy. I guess what Volta lacked in material wealth, he more than made up for in middle names. At first, the young Alessandro was a dull-witted child, it seemed. It was not until this 4th year that he began to speak. But soon afterwards, he advanced extremely rapidly in school. He showed a flair for foreign languages, of all things, even though he didn't speak when he was very young. He began experimental studies on electricity when he was still a teenager. He gained great fame for his invention of the electrophorus. That was a device that held electrostatic charge and then was able to transfer it from one object to another. This illustrated many of the basic principles of electrostatics and was very important in its day. Shortly thereafter, he was offered a professorship of physics at the University of Pavia, and that's where he spent the rest of his career. Now, Volta's most important contributions followed discoveries of his fellow countryman, the anatomist Luigi Galvani, who lived from 1737 to 1798. Galvani focused much of his work on the subject of animal electricity. That's the kind of phenomena as exemplified by the electric eel, but animal electricity was believed to be held by virtually all living things to one extent or another. Galvani was born in 1737 in the northern Italian city of Bologna. There he was raised and educated all the way through a medical degree. He went on to become a faculty member at the University of Bologna and president of the Bologna Academy of Sciences. So Bologna was certainly his home. He spent his entire career there, and he died in the exact same house where he was born, of all things. Luigi Galvani became an authority on physiology, especially on dissection. And he was fascinated by the interaction of tissues with electricity. So he liked to subject various kinds of tissues to electric charges, electric shocks, and see what happens. His most famous experiments involve studying the effects of electric sparks on the muscles of legs, of frogs, the very muscular legs of these frogs which you've seen that allow the frogs to leap and kick so hard. He discovered the remarkable effects of static electricity which causes the legs to twitch and convulse spontaneously, even from a dissected frog. While performing these experiments, he noticed something rather new and unexpected. What he had done is he attached a brass wire to a frog's leg, and he was preparing to induce a spark by touching the legs with a steel scalpel. And here's a quote from one of his papers. "While one of those who were assisting me touched lightly and by chance the point of the scalpel to the internal crural nerves of the frog, suddenly all the muscles of its limbs were seen to be so contracted that they seemed to have fallen into tonic convulsions. But the thing is, these convulsions were not caused by a spark. It was an entirely new phenomenon because this was occurring just because there was a brass hook in the frog and a steel scalpel touching at the same time." In another set of experiments, Galvani wanted to study the effects of lightning on severed limbs of various kinds of animals. So he suspended an iron wire across the courtyard of his villa, and then he had brass hooks which held the limbs to the wire. Well, the nerves of the various organisms were attached to the iron wires directly. So here you had brass and iron, again, two different metals stuck into these severed limbs which were hanging outside. When he placed the wire outside during an electrical storm, the various limbs would jump and twitch as he expected. But curiously, the twitching sometimes occurred on dry days, on sunny days, just as long as the brass and the iron were both attached to the limbs of these frogs. Lots and more experiments were required to kind of clarify and define this phenomenon. Galvani showed that when copper and iron wires were inserted into different parts of these dead frogs' legs, the two wires were then touched together, and that's what caused the legs to convulse. You didn't need a spark, you didn't need any sort of other electrical current, you just needed two pieces of metal. This was a new kind of electrical phenomenon. The anatomist Galvani interpreted this phenomenon in terms of animal electricity. He said this is an electricity that's intrinsic to living organisms, to biological tissues. Others wondered whether Galvani had actually discovered the life force, which had been much debated at the time. Others had to study this phenomenon as well. Upon hearing of Galvani's experiments, the physicist Volta directed his attention to these same phenomena. So he tried the same kinds of experiments. But he focused more on the metallic elements of Galvani's experiment than the biological components. After all, he was a physicist. He was interested in the physical world, and so metals seemed to be the more basic thing to study to him. He soon became convinced that it was the juxtaposition of these two different metals that led to the electrical phenomenon, which he then called metallic electricity. He found that different pairs of metals produced different degrees of the effect, and there's a very clear sequence. This sequence, which is known as the electrochemical series, starts with zinc at one extreme, followed by tin, and then lead and iron, copper, platinum, gold, and silver. So the farther apart in that electrochemical series you have two metals, the greater the effect, the greater the twitching of a frog's leg, for example. At this point, a very unfortunate feud developed between supporters of Galvani on the one hand, the idea of animal electricity, and Volta's metallic electricity. And the lines were divided very cleanly. An extension of this conflict was between biology and physics, which would take the primary role. And as so often happens in science, it's the physicist who seems to win out over the biologist. Volta's view soon prevailed, because his electrical effects could be produced independently of frogs' legs, or any other biological material for that matter. He found that if you put two rods of different metals into an acidic bath, just a chemical bath, an electric potential would form between those two rods. So you could actually create electric sparks or other electrical phenomena just by putting two pieces of metal into that acid bath. This electrical potential that was created is quite analogous to the gravitational potential of water behind a dam. In other words, you're storing electrical potential energy by having these two pieces of metal in an acid bath. Just as if you release some of the water, you release gravitational potential energy. So by touching the pieces of metal together, you'd release some of this electrical potential energy. You can do work with those moving electrons, with those moving electric charges. And this was the beginning of the study of electricity, the study of moving electrons. For Volta, the next step was a very logical one. It was to devise various arrangements by which you place different metals in contact and study various configurations. He found that he could produce electricity just by stacking alternate layers, alternate plates or disks of metals, such as silver, zinc, silver, zinc, silver, zinc, in a saltwater bath. This device was described in 1800 in Volta's article on the electricity excited by the mere contact of conducting substances of different kinds. This was the invention of the battery. Of this battery, he wrote, "The apparatus to which I allude, and which will no doubt astonish you, is only the assemblage of a number of good conductors of different kinds arranged in a certain manner." And that certain manner was to alternate plates or disks of material, two different metals, and keep them in some kind of solution, an acid bath or salt water or some such thing, which would allow the current to flow. Volta's battery marked a turning point in the study of electrical sciences. For the first time, researchers could rely on a steady source of electricity, a reliable source of electricity that continuously flowed, as opposed to transient sparks and discharges of the kind produced by a friction machine, for example. Surprisingly, Volta's very first experiments were not on an inorganic physical system, but rather on the human body itself. For example, he tried his electrical effects on the tongue. He said that when you apply the two electrodes to your tongue, you sometimes tasted a strange bitter taste. If you put it near your eye, you saw flashes of light. Pain and convulsions could also be produced if you put the electrodes in certain parts of your body. So he experimented on humans. He also experimented on many animals. And he also wrote, for example, "It is very amusing to excite in this manner the chirp of a cricket." So not exactly our modern thinking of how we should use electricity, but it was the type of experiment that Volta could perform. Other investigators carried these kinds of experiments to extremes. Human corpses were made to kick on a table, even to sit up when you attached batteries to the appropriate muscles of a dead human being. These bizarre demonstrations, I think, must have contributed to Mary Shelley's Frankenstein, which was written about the same time in the early 1800s. And that, of course, raises real serious questions about what are the appropriate limits to scientific research. If you read Frankenstein, you realize that's one of the underlying questions of that book, and one that faces us still today. It was Volta's experiments on electricity and applied to human cadavers and so forth that must have raised these doubts in many people's minds. Volta's experiments also contributed a great deal to the development of electromedical devices, especially home remedies, which were by the end of the 19th century available in huge numbers. Just in a Sears Roebuck catalog, for example, you could go and you could buy home energy devices, little portable devices where by turning a crank you would be able to produce electric charge, and then you'd have two electrodes which you could place on various parts of your body, perhaps to soothe headaches or other muscle aches of various sorts. I don't know if they worked, but they certainly were sold in large numbers, and it became conventional wisdom that electricity was one of the ways of curing the human body. Volta's battery and its successor proved invaluable in chemical research as well. Within weeks of its announcement, there were British chemists, two British chemists, William Nicholson and Anthony Carlisle, who constructed their own very crude battery. What they did is they took 36 silver coins, silver half crowns, and they interspersed them with 36 discs of zinc. So they had a silver zinc battery, and they immersed this into an acid bath, and they were able, with their very crude battery, for the first time to break water, that's H2O, down into hydrogen plus oxygen. So this was a very important way for chemists to understand the constituents of nature. Batteries were also used to decompose many minerals and other substances. This led to the discovery of many new elements, as we'll see in Lecture 20. Larger and larger batteries were built with more and more pairs of metal plates, larger and larger metal plates. The flamboyant English chemist and science lecturer Humphrey Davy constructed a mammoth battery with 2,000 double plates. He did this at the Royal Institution to make a huge public demonstration. This array was extremely dangerous. It filled an entire great hall and, of course, produced a huge voltage, a very, very large amount of electrical energy. In 1810, Davy became the first person to demonstrate electric lighting when he vaporized rods of charcoal and platinum and other material in blinding incandescent displays. So he'd hook up his battery to these pieces of material high above the auditorium or high above this floor, and they'd burst into flame and create a blazing light for as long as they were able to before they just vaporized. When you pass a strong current through any material, it can heat up, and the same principle is used today in electric arc welding, as well, of course, in light bulbs where you pass a current through a very thin filament, which then glows very, very hot. Let's talk about electric circuits, because that's where we really use electricity in our lives today. The battery introduced a new field of research on electric currents and these things called electric circuits. An electric circuit is a very simple concept. It incorporates three different components. Every electric circuit is like this. First of all, you need to have a source of electrical energy. You need to have a power plant or a battery or something else that generates electricity, allows electrons to move. So you have to have that electric force to push electrons along. The second thing you always need is a device. A device is something that does something interesting, does something useful when you put electric current through it. A light bulb, a heating element, a semiconductor array that operates your radio or your television or some other electronic device. Those are the devices. And then finally, you need to have a closed loop of conducting material. Usually, the closed loop is completed with a piece of wire. So let's look at these different components more carefully. That source of electrical energy, of course, you can get a battery, you can get a solar cell, hydroelectric plant. You always have to have a place where there's a positive terminal and a negative terminal, and charge then can flow from one to the other. This push of electric charge is called voltage, and you measure this potential in volts. The second component, the device. This word device has a very special meaning in the study of electricity. A device is something that uses that electric energy to do something. It responds in some interesting or useful way to that electric current. In the case of 19th century physicists, most devices were designed to display some interesting phenomenon, for example, in a classroom environment or in a laboratory environment. So composing water, decomposing water, essentially your water becomes the device in that case, something that glows. Even a frog's leg can be thought of as the device in those early experiments. But today, of course, devices are anything that you'd plug into a wall socket and use with electricity. Then you have to have a piece of conducting material. And while it's usually a wire, there are certainly other kinds of materials that can close a loop. And if you look inside your television, you'll see various strips of metal that have been deposited onto a plastic surface. They may be the conducting material. Or even, in some cases, the chassis of a device becomes part of the closed circuit. And we'll see how that works. A very simple, everyday example of a device of this sort is a flashlight, which incorporates all three of these components. You can unscrew your flashlight. You see the source. In this case, it's two batteries. Typical batteries of this sort are about 1.5 volt. So two batteries together provide you 3 volts of current. The device is the light bulb, which occurs at the end of the flashlight. Current flows into this light bulb. It goes through a very tiny filament, and that filament, because of electrical resistance, heats to a very high temperature and therefore glows brightly. And finally, the circuit is completed by a strip of metal which goes down the side, the barrel of the flashlight. You'll also see a coil of wire, usually at one end of the flashlight. At the other end, you'll see the contact points for the battery and the other strip of wire, and so you have a complete circuit when you put the whole flashlight together. Flashlights and most other electrical appliances also have a switch. A switch is merely a device that when you open and close it, you're breaking the continuous loop of conducting material When the switch is open, you don't have current flowing, but when the switch is closed, you do. And basically all circuits are of this sort. Even the circuit you plug into the wall, there's a continuous loop of wire that extends from your home all the way to the power plant. That's the complete circuit. The flow of electrons through an electrical circuit is called the electrical current. Current is measured in amperes after the French physicist André-Marie Ampère, who lived from 1775 to 1836. 1 ampere corresponds to about 6 billion electrons passing a point in that circuit every second. So you're literally talking about the flow of electrons. Current is the flow, it's the movement of electrons, and if 6 billion electrons pass a point in the wire every second, you have a current of 1 ampere. You've probably used this term in conjunction with fuses or with circuit breakers. We use fuses in our homes because if you have too much current being pulled through a wire, the wires can get hot. So in order to protect your house from burning down, you put a fuse, you put a circuit breaker in the way. A fuse is designed to burn up if the current gets too high. So for example, in a 30 amp fuse, if the current gets up to be 35 or 40 amps for any extended period of time, the fuse will burn out and then you'll have to replace that fuse, but that's better than having to replace your entire house, I suppose. Then we come to the electrical potential. You have to be able to push electrons through your wires, and you do that with the electric potential, which is measured in volts, in honor of Volta. Remember, voltage is a form of potential energy. It's the energy that's the ability to exert a force over a distance, and you're pushing a force on those charged particles, on those electrons. The higher the voltage, the bigger the acceleration of your electrons. Typical flashlight batteries are 1.5 volts. You can buy hobby batteries that are 9 volts or 6 volts sometimes. The typical voltage in a wall socket could be 115 volts, for example. So we have lots of different voltages, and you will often see in your appliances that they're rated for certain voltages. A third component of every circuit is resistance. Every circuit has some resistance to the flow of electrons. Electrons collide with other electrons in the atoms that make up the wire, and they thus convert some of their energy to heat. This is part of the second law. You just can't have any transfer of energy from one form to another without inevitably losing some of that energy as heat, and this is a case in point. As electrons flow through the wire, some of that energy that you're paying for in your electric bill is converted to the heat just in the wires. Resistance is measured in ohms. That's after the German physicist George Ohm, who lived from 1787 to 1854. Once again, this classic period of the study of electricity, the first half of the 19th century, and that's when Ohm did most of his important work. Ohm discovered a very simple relationship among current, voltage, and resistance. In fact, that is, current is proportional to voltage and inversely proportional to resistance, or V equals I times R. Voltage equals current times resistance. You can actually buy a device in most hardware stores called a multimeter. A multimeter can measure resistance, it can measure current, it can measure voltage of any particular set of components in your electrical device. So it's an extremely useful and compact device. We need one other term associated with electricity, and that's power. Recall that power is defined as work divided by time. In an electrical circuit, then, power is the current times the voltage. It's measured in watts. If you see light bulb, if you see amplifiers, they're always rated in watts. That's the amount of power that's consumed. The higher the wattage, the faster the energy is consumed by that object, be it a light bulb or an amplifier or whatever. Power equals current times voltage. In our homes, the energy source is typically a power plant that's many, many miles away. A few homes have their own portable gasoline generators in case there's a power failure, but most of our electrical energy comes from remote sources. Electricity is carried over power lines, and these power lines link most of the United States in one gigantic network, one gigantic circuit that's all interconnected. This physical linkage, I think, is one of the most dramatic and transforming events of the last century. The separate circuits in your home feed off this one great network that's nationwide. Let me tell you about two kinds of different circuits that you find in your home and in other common devices. These are called series circuits and parallel circuits. In series circuits, you have several devices, each of them linked up one after another in just a single large loop. The same current flows through every device in that circuit, though the different devices in general are going to have different voltages across them, because the voltage changes as you go along that circuit. If any one of the devices in a series circuit is broken, the whole circuit fails. And I can show you that effect in a little device here. Here we have 3 light bulbs connected in series, in just one loop of wire connected to a battery. If you unscrew one light bulb, the whole circuit fails. Screw that light bulb back in and it works. You remember Christmas tree light chains that are like this. One light burns out and the whole chain of lights is useless. That's a series type of circuit. The other kind of circuit is called parallel circuit. And in this case, the different devices are arranged so that a single source supplies voltage to separate loops of wire. Every device sees exactly the same voltage, but in general, the different devices are going to see different currents. And each device is going to work even if the other ones fail. So there's a slightly different strategy here. You can show this in the same way. Here are 2 light bulbs linked up in parallel. 2 lights go on. If I unscrew one light, the other one works. That's a parallel circuit. And that's the way modern Christmas tree lights are usually done. So even if a single light burns out, you don't have to throw away the whole strand. There's a way of systematizing all these relationships between circuits that are called Kirchhoff's laws, extremely important in electrical engineering. They systematize the behavior of circuits. The first law is just a restatement of the law of the conservation of energy. It says the energy produced by the source, a battery for example, equals the energy consumed in the circuit, including the heat that's lost as a result of resistance. The second law then is a statement of the conservation of current in an electrical circuit. It says the current flowing into any junction equals the sum of the currents flowing out of that junction. And this is pretty logical because current is just a matter of electrons flowing through the wire. So the number of electrons flowing into a junction equals the number of electrons flowing out of that junction. This word electricity, it's been introduced in so many contexts here. We've talked about animal electricity. You talk about metallic electricity, static electricity, lightning, and so forth and so on. But you might ask yourself, are these different forms of electricity the same, or are they somehow fundamentally different? That was another question addressed in the 19th century. And it was Michael Faraday, the great scientist Michael Faraday, who we've talked about and we'll see more in the next lecture, about who made very careful systematic surveys of all these different kinds of electricity. And what he did, he was able to show that all of these different forms of electricity produce exactly the same kind of phenomenon. They all produce sparks if you treat them in the right way. They all can flow through wires. They all can be made to do work. And indeed, it was Faraday's research that for the first time showed that animal electricity of an electric eel, the electricity coming from a battery, the electricity of lightning, all these phenomena were one and the same, and indeed we now know they all result from the movement of electrons. Let me summarize this lecture on electricity. The science and technology of this phenomenon of electricity was begun by the development of the battery more than 200 years ago. It was initially nothing more than a stack of alternating plates of metal. But the battery provided a steady source of electrical energy that could be used to move electrons from one place to another. It could be used to make an electrical circuit. And we saw that there are 3 components of all electrical circuits. First, you have to have a source of energy like a battery or a power plant. And then you have to have a device like a light bulb or a heating element. And finally, you need to have a complete loop of conducting material, usually made of wire. These were great discoveries. But it was the great and startling unification of electricity with magnetism that transformed the world's technology. And that's the subject of the next lecture.